I'm Felipe Bivort Haiek, and this is part of my master's thesis at the Universidad de Buenos Aires, and the title is Towards a Machine Learning Prediction of Electronic Stopping Power. This is the team of people I work with. They are physicists. And well, I will give you a brief introduction to what is stopping power, and then the nuisances we have to deal with in the database. And I'm going to talk more about a particular model that we made that is for monoelemental targets, and then one for molecular targets a little bit, and some preliminary results about that one. Okay, so what is electronic stopping power? Well, let's first define stopping power. So stopping power is what happens when you have an ion and you launch it into a target. Yes, and so it's the energy lost per unit of longitude when that ion penetrates the target. And if you look at the image in the right, you will see that there is a nuclear part, yes, that is caused by the nucleus of the ion bumping with the nucleus of the target. And there is also an electronic part that it has to do with interaction between the electronic clouds. And if you go to mid to large energies, it's the part that wins. So that's why we're interested more in that part. And why one should study electronic stopping power? Because, well, it has plenty of applications. One is, for example, in proton therapy. Yes, in proton therapy, what you want to do is you throw an ion into the human body, and you want it to end up in the tumor and release all the energy in the tumor and not in other places. And this is quite better than doing, for example, radiative therapy, because when you have light, the X-rays go through all the body, and you cannot really define where the light will stop. It will go through all the healthy tissue as well as the tumor. And another important application that is of interest to us is to do the semiconductor doping. Yeah. So basically, you need to know the stopping power of the impurity that you want to insert into the material. Okay. So the database we used was a database from the IAEA. It's composed of data from publications from more or less the 1920s up to now. So it has a long range of different data from different publications with different experimental techniques. Also, another problem that you have that you can see there is that different publications will say different stopping powers for the same energy. And another very important problem is that you cannot use the same measuring apparatus for different energy ranges. So really what you have is like different curves at each part. And well, another problem is that some of the data and the database was maintained manually, so there were like many issues to resolve there. Okay, so for data cleanup, we tried many things. What worked was this heuristic. This heuristic has 3 main points. We want to remove preferentially all data because we think that the techniques have improved with time. Then we want to remove only data from energy ranges where there are better candidate points. Yes, and if we have a little amount of data in that energy range, we want to leave it because we cannot say, well, we'll replace it with a new one. Another important part is that we only want to remove data that is isolated. Yes, so to know if data is isolated or not, we use the DB-scan clustering algorithm. And the idea is that if the data points are clustered, that in some sense will give an idea of the noise and the error that is intrinsic in the measurement. Okay, so here are some cleanup results from some ions and targets. In the top you have hydrogen in copper, and in the bottom you have hydrogen in zinc. If you look at the bottom row, you can see that at the beginning we have like 3 different bell curves, and after we apply our heuristic, we get only 1 bell curve that is well defined. Okay, so after cleaning the data, we created a model. First of all, a model that only deals with monoelemental targets, that is targets that are made from only 1 element, that is around 60% of the full database. And for that, we use a fully connected network. We added a lot of dropout because of noise issues. And well, I'm obviously ReLU activations. To measure how good the model was, we use the mean absolute percentage error. Yes, because we want the prediction to be good all along the different energy ranges. And what we do is 5-cross validation, and to select features that were from different physical features that we had to choose. So in the end, what we chose was the atomic number for the ion and the atomic number for the target, the mass of the ion, the mass of the target, the logarithm of the incident energy, and the first ionization of the target. Yes. And for the model to be stabilized and to train well, we had to do like a bunch of tricks. One important trick, for example, was like removing the bias from the first layer of the neural network, because if not, you get very unphysical results like the one in the left. You have very good overlap between the prediction and the measurement, but when you go to like really low energies where there is nothing measured, you have like this bump over there. So to solve it, you need to get rid of the bias of the first layer. Okay, and then what we did is compare with the best model that is currently used by physicists and engineers, that is SRIM, and our model is called ESPNN. What we did was, SRIM was basically trained. It's not really a trained model, but let's say that. It was only using data up to 2013. Okay, so what we did to be in an equal footing was also only train our model with data up to 2013, and then what we did was check the MAPE metric for different test sets and for different ions, and we find that we win against SRIM in all of them. Okay, that's all for the monoelemental model. I'm going to talk very fast about the molecular model. For the molecular model, we care about the structure of the molecule. So if we want to use the structure of the molecule, we need to consult the database to get the structure of the molecule out. So for that, we use PubChem. From PubChem, we deambiguated the names that we have on the database. We get an INCI key, and from there we consult either materials project or the quantummachine.org that has the QM9 database. And from there, what we did is reuse this model that is SCHNET, that is used for predicting different molecular quantities. And what it's nice about it is that it has an embedding for each atom. And if you take the activations from the last layers, you will have not only the embedding for that atom, but also information of all the environment of that atom. So, and what we did there was we take the last layer, the activations for the different atoms, and then what we do is add all the embeddings, we add all the information that we have before, and we do that per atom, and we put it again on a fully connected network. And these are our preliminary results. We're still doing better than SRIM, but we think we can still do better. And to do better, what we want to try to do is try to see if we can fine-tune the whole SCHNET architecture, or either improve on the molecular model, trying more features, or use the phase of matter information there. So, well, thank you.